Next up, we have an innovative research project that can capture mechanical energy from waves and convert it to electricity. Please welcome the Ocean Energy Research Team.
Good morning, ladies and gentlemen. Thank you for coming out today. I'm Stephen Helkin, a mechanical engineering student pursuing my master's here at UCF. And today we're going to present to you an innovative design in which we can capture renewable energy using ocean motion.
Hello everyone, my name is Carlos Velez. I'm an aerospace student here and pursuing a graduate study in thermal fluids here at UCF. You can see our photos there in our majors. Wave energy isn't new. It's been around for a while. It began in the oil crisis when the government started pushing for natural energy technology. Although it lagged behind in wind energy and solar energy due to material. Since the water is very corrosive, you need a special kind of material to keep a mechanical device safe and prevent any rusting. Ocean wind energy definitely has the most harnessable energy out of the other natural energy sources. For a 1 meter high wave, you could produce 9.5 kilowatts of power per meter of shoreline. So water definitely has a lot more strength than versus wind turbine because it has 1,000 times greater density. So it's going to push 1,000 times harder on any turbine blade, or in our case, a buoy, to harness energy. And in the total world, you could produce 800 gigawatts of power available from wave energy. And as you can see here, we've marked a couple places in the world where wave buoys and wave farms are being created. As you can see, we have zero, pretty much in Florida. We're trying to bring some of that technology here. So Stephen and I have been working on a research project these last 20 months to design a mechanical device that you would install inside of a buoy, and it would convert the motion of waves into electrical energy. Basically, as you can see here, we have a shaft connected to a generator and cables which drive the shaft. These cables would be moored down and essentially connected to the base of the ocean, so that when the buoy rises, it brings this mechanical system with it, and that chain forces the shaft to spin. As the shaft spins, it turns the generator, and we create electricity. We use a couple components to improve the efficiency of the design. We incorporate 2 sprockets which allow us to turn the shaft in one direction even if the buoy is rising and falling. So this way we can harness 2 strokes of energy versus just the upward motion. Additionally, we've added some flywheels to keep the momentum going and try to eliminate any startup torques and keep the shaft always in continuous motion. And of course a permanent magnet generator, which Stephen will describe the load control system we designed for it.
Thank you, Carlos. Excuse me. Thank you, Carlos. So this design that we just presented is only the mechanical system of the project. We are going to go into developing a buoy in which we can use in the ocean environment further, but for right now, we need a method to assess the performance since we can't place it in the water. So what we use is we have a motion platform that simulates wave motion. It's able to heave the buoy upwards and downwards, sort of essentially simulating the way that the buoy will be moving in the ocean environment. And so right now we have an average power output of about 238 watts, which exceeds our original expectations. But what this means is that over a year period, this will produce about $210 worth of electricity. That's not too impressive. However, because the motion platform is only able to move a certain amount, this number reflects only a 10 centimeter amplitude of wave. That's certainly much smaller than the wave that we're expecting to be using. So we expect, if you go next slide please, we expect with optimization and different methods, we get around 1.6 kilowatts for a 1 meter sized buoy and about 1 meter amplitude wave. We had to develop a significant mathematical model to simulate this, and different parameters were able to be optimized, such as the radius of the buoy, the size of the flywheels that Carlos had mentioned earlier, and different other parameters, such as the electrical loading on the system and other options such as that. And with that, we're able to adapt to the ocean environment. We're not limited to, let's say, this area where we have waves this high. We're able to adjust different parameters and such. And because our buoy is designed to be very small, it'd be easy to become a wave farm. Using maybe about 100 buoys in this wave farm would produce enough power to empower 1,500 homes. Now, so the next step is actually using the optimized things we have obtained from our mathematical simulation and producing a new design. And with this new design, we'll be able to develop a buoy that would be able to harness, that will be able to place in the ocean environment, which is, as Carlos mentioned earlier, a significant challenge, but we look forward to facing it. So we'd like to thank our advisors, Dr. Kurt Lin and Zhiha Chu, and also our sponsor, Florida Energy Systems Symposium. If you have any questions, we encourage you to come visit us. Our booth is the fourth one over on that side. And thank you so much for your time.
Thank you.